Good morning. So we are moving on to the next chapter. Don't know the chapter number, doesn't matter. Depends on which text you're using. Which are Newton's laws. Let me talk a little bit about Sir Isaac Newton. Newton lived in between 1642 and 1727. Interestingly, he was born in the year that Galileo passed away, 1642. And Newton is known for giving Galileo a lot of credit for his work, actually to the extent that you've probably heard the quote, "If I have seen farther, it is because I have stood on the shoulders of giants." And that quote is from Newton, and interestingly, it's a really interesting history, that Newton said that in actually a context which is very different than people realize. He said that in an argument, in a letter, I believe, to the Royal Society in London, in response to a conflict he was having with Robert Hooke. You might have heard of Robert Hooke before. If you've taken some science, I believe he is known a little bit in chemistry perhaps. But anyway, Hooke, this is Hooke as in Hooke's law for springs, if you've learned that before. And Robert Hooke and Newton were contemporaries. Robert Hooke and Newton worked worked in parallel on forces and motion. And certainly Newton is known for a lot more than forces, but that's what we're going to talk about in this chapter. He's known for gravity. He's known for optics. That's one thing that people often forget, that Newton published a lot in optics. But Newton and Hooke were working on the same things. And it's unclear that Newton figured out everything first, but Newton's given a lot of credit. Hooke is only given credit for F equals minus kx in physics. That's the only place you see Hooke. Hooke's law for springs. But Newton's given credit for significant everything that we do in forces and the connections to the motion, although Galileo did a lot of that kinematic stuff. But Newton said, "If I have seen farther, it is because I've stood on the shoulder of giants," because Hooke was claiming that Newton was cheating, essentially, was stealing his things, was building on Hooke's work, and Newton wanted credit for it. Newton didn't want Hooke to have credit for it. This was an academic argument. It was who came first, who got the information, who figured it out first, and it was a real what do you call it? A fight. Fight is not the right word, but it was a real argument between them in the Royal Society about who figured stuff out first. And Newton, in one of these arguments, said about Hooke, "If I have seen farther, it is because I have stood on the shoulder of giants." What he meant was that he was building on what Galileo did and not what Hooke did. And it truly was meant as a criticism of Hooke, because Hooke was not a tall man and Galileo was. So he was literally referring to the height of the men when he made that comment. So it's a really interesting out of context quote. And basically, Sir Isaac Newton won out on this academic argument primarily, and there's a lot more complication than this, but primarily because Hooke died before Newton. Hooke passed away, I don't remember what year, we could look it up, but and Newton basically didn't publish any of his treatises on motion, on forces, until after Hooke died. So Newton got credit and Hooke didn't. If Hooke didn't die so young, perhaps these would be called Hooke's laws instead of Newton's laws. Another interesting story about Newton is that he was working at? Well, anyway, he was at Cambridge University, and he was sent home during, of all things, a global pandemic. He was sent home. The university had to close, believe it or not, because of, global pandemic, local pandemic. I mean, you didn't have airplanes back then. But because of a pandemic, the university was closed and he was sent home. And this image is of him sitting in his mother's garden. And this is indeed where Newton came up with his law of gravitation. We will not study his law of gravitation until a later chapter, but Newton acknowledges that it was when he was home from university that he was sitting in his mother's garden and he was watching the apples fall from the tree, and he realized something about gravity. He realized that the reason why the apple fell from the tree was the same reason why the moon rotates around the earth, which was the same reason why the earth rotates around the sun, that those were all just different forms of gravitational attraction. And so the cartoon image is always of Newton sitting under an apple tree and an apple falls on his head and boing, he gets an idea. In reality, it was Newton sitting in the garden considering the apples falling. I'm not entirely sure he was sitting under a tree and something fell on his head. But Newton himself likes to tell the story about, or liked to, was quoted as telling the story about, in his older age, he would tell the story about sitting in his mom's backyard and pondering the apples, as in this image. I just looked it up, and Robert Hooke died in 1703, so 24 years before Newton died. So I spent a few minutes talking about Isaac Newton because Isaac Newton is certainly looked at as one of the more important figures in all of physics. There were many, many people who built the physics that we know today prior to Isaac Newton, but Isaac Newton is really the last person to get it right? He had to people before him helped to build the structure that is known as physics, but Isaac Newton really fixed it and got it right. Now, it's not entirely true that Isaac Newton got it all right. Isaac Newton got a lot wrong, and people have fixed it since then, but we still use a lot of the gravitation, the forces, and the optics that Isaac Newton published. And of course, the other big figure, and again, there's so many figures in physics who have built the physics that we know. Of course, the other big figure is Einstein, but Einstein and Newton are the two big ones in physics, which is why I spent a little time talking about Newton. And so in this chapter, we're talking about what are known as Newton's laws. Newton's three laws. And you can and often you can think of Newton's four laws as in the fourth law being his law of gravitation, but we're not talking about the law of gravitation here. So we're going to talk about Newton's three. I might have cut myself off there. We're going to talk about Newton's three laws. And from now on, I will just refer to them as N1, N2, and N3 for short. Whoops, that's not N1, N1. So let me ask, most of you know, and many of you have taken physics before, but most of you have heard of Newton's first law. What is Newton's first law? See if you can come up with it. So Newton's first law is an apple a day keeps the doctor away. No, just kidding. So Newton's first law is a body in motion will stay in motion until a net force is exerted on it. A body at rest will stay at rest until a net force is exerted on it. I tried to come up with the most sort of general form that you might have seen it in before, but I do want to be very careful and say that really the law is more than this. You need to understand the details here. When we say a body in motion will stay in motion, or when Newton says that, what he meant is that it will stay in motion at a constant speed in a straight line. At a constant speed in a straight line. And that really means that it's staying in motion at a constant velocity. So a body in motion will move at a constant velocity until a net force is exerted on it. A body at rest will stay at rest until a net force is exerted on it. Staying at rest, a body at rest, v equals 0, that is a constant velocity as well. So really, Newton's law can be written as a body will stay at constant velocity until a net force is exerted on it, period. That is Newton's first law. Now, we will talk in a little bit about what property of a body gives it, allows it to follow Newton's first law, and that property is called the law of inertia. And we'll talk about what inertia is in a little bit. Law of inertia. Newton's first law is the law of inertia. A body has inertia. It'll keep its motion because of the inertia that it has. So let's go ahead and take the first law and think about it in equation form. So you really should be able to, it's a word problem, right? You take it and you put it in equation form. You say a body will stay at constant velocity. So we're saying that v equals a constant until a force is exerted. I guess, whoops, hold on. There you go. Force we've already discussed is a vector. We haven't defined force specifically yet, but if we have a net force, and we haven't defined, we'll talk about this later. V is a constant until F net equals 0. What that means is, therefore, if F net, the net force on a body, is not equal to 0, therefore acceleration is not equal to 0, because that's what it means for velocity to not be constant. If velocity is constant, I guess I should have said velocity is constant, therefore, that means A equals 0 if velocity is constant, right? Velocity is constant means the acceleration is 0. So if the acceleration is not 0, there must be a net force on it. That's what I'm trying to say. That's what the first law says. If the acceleration is not 0, there must be a net force. And Newton's second law tells us the relationship between these two things. If the net force is not 0, the acceleration must not be 0, and what Newton's second law tells us is the net force is proportional to the acceleration, but with a proportionality constant, which is the inertia or the mass of the body. We'll again talk about inertia versus mass in a second. So Newton's second law tells us that the net force is proportional to the acceleration. It tells us the relationship that the first law gives us with the proportionality constant of mass. F net equals ma. This is really Newton's second law. It's just first law in equation form. N2. So do you know Newton's third law? Think about it for a second. I'll go ahead and write it down. Newton's third law is for every action, there's an equal and opposite reaction. So you got to look at this law and say, what is the physics going on here, right? Because we've so ingrained this concept in our lives. I think all of us have heard this statement before. And really you think of it as a moral statement in a way. It's sort of a moral statement, right? If I do something bad, then then they're going to do something bad back to me. If I do something good, then they can do something good back to me. If that people react to actions. And that's a good moral compass, right? That people react to actions. But the fact is that when Newton said this, that's not what he was talking about. He's talking about a specific physical law that we can apply this to solve for forces and situations. And the reason why that's not obvious is because Newton lived at a different time when language was a little bit different. And action and reaction literally mean forces. So really what in our language, what this means is the more physicsy law is for every force, there's an equal and opposite force. Now, again, you got to be really careful here when you're applying this law because sure, and we haven't defined force yet, but we will next. For every force, for every time you push something, you can always find somewhere in the world there's some equal and opposite force. But what Newton meant is a very specific, there is always a very specific force that is going to be due to the fact that you're exerting the first force. There is going to be a reaction force in the same situation, which is equal in magnitude and opposite in direction. Equal in magnitude and opposite in direction. So we will talk about how to identify that. But they're called, the particular two forces that we're talking about here are called a third law pair. So you can always find two forces that are equal and opposite, but they're not necessarily Newton's third law pairs. So we can talk about a third law pair of forces, and we'll talk about that later. We'll just spend time on that later. So that's an overview of Newton's three laws. What we'll do next is we'll carefully define force, and then we will take Newton's three laws individually and spend a little time with each of them.